Saliency Maps. This is one of the simplest and most important interpretability techniques in deep learning. Since we have already talked about the CNNs, gradients, and receptive fields in the past videos, what Saliency Maps problems are solving. So imagine we have the image dog or dog image, and the convoluted dog, that the image is dog 99.8%. But when someone asks why did the model say it's a dog, so the CNN doesn't explain itself. Inside the model it only sees numbers. So those are just pixel values. So the question becomes, which pixels were the most responsible for predicting dog? That's exactly what Saliency Maps answer. So we are looking for the pixels the most responsible for the predicting dog. Why it's predict a dog? So what we're looking for the pixels. So interpretability means understanding why an AI model made a prediction. Instead of treating a neural network like a black box, like from image to convolutional network and it predicts dog, we want to open that box, like from the image to convolutional neural network and dog, and which pixels cause that predictions. And why do we need interpretability? So first is trust. Imagine AI detecting a cancer. Doctor asks, why did you predict cancer? Instead of blindly trusting the model, we can inspect what the AI focused on. If highlighted region is actually the tumor, that is more trustworthy. Next, debugging. Sometimes the model is correct for the wrong reason. Example, in the previous laboratory, like we have the wolf image and its background is snow. The model says it's a wolf. And later we discovered that it wasn't looking at the wolf, it was looking at the snow. Because a lot of image that we fed during the training has the snow background of the wolf. That's why it says a wolf. So the model learned if there is snow, there's a wolf. Instead of wolf features, that's wolf. Saliency Maps help discover these mistakes. So next is discovery. Sometimes the model notices patterns human never realized. Example, medical images. The doctors might overlook tiny textures, and the AI discovers these tiny structures are actually useful. Interpretability reveals those discoveries. Next is ethics. Maybe the model behaves differently depending on skin tone, age, or another group. Interpretability helps reveal bias before deploying the model. Next is Saliency Maps. Now we comes to the main idea. Imagine the dog image. Suppose we slightly change one pixel. So the question, does the prediction change? If changing one pixel changes the prediction a lot, that pixel must be important. But if changing another pixel and changes almost nothing, that pixel isn't important. So that's the idea of Saliency Map. So if I slightly change every pixel, which ones matter most? So bright pixels is important, dark pixel is not important. So how does PyTorch know which pixel matters? Here's a clever part. It uses something we've already learned, the gradients. During the training, gradients are usually computed for weights, like weights, and then calculate the loss. And gradient answers, if the weight changes, how much will the loss change? But now, we are not interested in weights. We want pixel and prediction. The question becomes, if pixel changes, how much the prediction change? So, as a gradient, the input. Normally, we compute loss to weight. Now we compute dog score and input image. Instead of the derivative score as the score change, how the weight change, or how the weight change, how the score change. We calculate If we change the pixels, how the score will change. So every pixel gets its own gradients. Can input have gradients? Yes, of course. So any tensor can have gradients, not only model parameters. If we tell PyTorch records grade true on the image, PyTorch will calculate gradient for every pixel. What does the gradient mean? Suppose one pixel has 12.4 gradient and another has 0.02. So the interpretation that 12.4 is changing the pixels slightly. Prediction change a lot. That's very important. And if you have the 0.2 changing the pixel, the prediction barely change. So here's the important note. So Saliency measures sensitivity to causation. Suppose this pixel is bright, it doesn't mean the model definitely look here. It means if this pixel changes, the prediction change a lot. That's a sensitivity, not proof of human-like attention. So why we use the model.eval? So before computing saliency, we write a code model.evaluation. Why? During training, some players behave differently. Example, we have the dropout, randomly removes neuron, batch normalization, uses batch statistics. If we compute saliency while those are changing, today's the gradients now will not be gradients in the future in the other steps. So we use the evaluation mode, so makes everything deterministic, exactly the trained model. So let's prefer the model like let's say we have the dog.jpg, we transform it like resizing, normalizing, and tensorizing them the model, exactly like inference. And one of the functions like compute Saliency map, inside it we use the input immediate clone that detach. Suppose our image was produced by earlier operations. So we have the image, we resize it, normalize the tensor. The tensor isn't live anymore because we have the process. So PyTorch won't save its gradients if the tensor isn't live anymore. If the first tensor, initial tensor, was changed by another tensor, that's not a live anymore. So we clone it, the tensor, the fresh copy, then detach it from the previous process. So we remove the computation history. Now it becomes live tensor. No one attach it. Exactly like the first, but have a different value. Step 2 requires the gradient true. It takes PyTorch to track gradients for this image. Now every pixel can receive gradients. So we do the forward pass. Okay. Suppose the output has the output like 0.01, 0.95, 0.3, and 0.01. Each number corresponds to one class. So let's select the desired class. Suppose we have 0.01, 0.95, 0.03. So the 0 in the output and 0 comma target class as a parameter here. The 0 means first image of the class, or the target class means the class you care about, example the dog. So we isolate 0.95. So step number 5, we do the backward. Instead of computing loss and weights, it computes dog score and input pixels. Every pixel now has gradient, and we retrieve the gradients, we do the input image grad. Now we obtain 3 channels. So each pixel has 3 gradient values, one for each color channel, indicating how sensitive the model score is to changes in the channel. These are activation sensitivities, not the original pictures. So the final visualization, those gradients are converted into the heat map. So let's say we have the dog and we overlay it to the dog. So the brightest regions are where the prediction is most sensitive. So the summary is this is the entire pipeline. If we have the image, we resize it, we normalize it, we have the lift tensor, and we have the request gradient true. We perform the forward pass, and we have the algo score, and select the dog score, and perform the gradient backward, and we have the gradient of input pixels. We visualize it, and have the saliency map. So since in feature extraction, is learn adjust texture parts or whole objects, and Saliency asks which input pixels most influence the final decision. In backpropagation, the same gradient computation used during training is reused here, but the gradients are taken with respect to the input image instead of the model weights. And the leaf tensor is cloned, the detached and requires gradient creates a new leaf tensor. So PyTorch will store gradients for the input image. And we have the output, and its parameter is 0 in target class. This selects the score of the class interest. Like for example, given is dog, and calling the dot backward to propagate gradients from the score back to the input pixels. So here's the key takeaways here. Interpretability helps explain why a model made a prediction, and the Saliency Maps shows which input pixels the prediction is most sensitive to. And it is computed as a gradient of the class score with respect to the input image. And we have the requires a gradient equal to true, enables gradient computation for input tensor, and we clone it, and the detached creates a new left tensor, so the PyTorch stores its gradients. And we have the output, and its parameter is 0 and target class, followed by the dot backward function computes gradients from chosen class score back to every input pixel. And bright pixels indicates high sensitivity, and dark pixels indicate low sensitivity. And Saliency Maps show sensitivity, not definitive proof what the model look at.